Welcome to another video from Lockdown Electronics with me, Bill, and this time we're going to take a look at using the signal generator with digital circuits, digital electronics if you like, and that's got some interesting things that we need to do to make sure we're producing a signal which is going to work properly with the circuits. So without further ado, let's go straight to the bench. Here we are with the breadboard then, and I've got 3 chips on here, and for the most part I've chosen them because I just happen to have them in my stash of 74 series logic chips. So what we've got is a 5-volt supply, and that red LED there is confirming the 5-volt supply is on. So first of all, let's just understand what's going on. Let's just make sure everything's working okay. So this chip here is a hex inverter. It contains 6 NOT gates. Here's the symbol for a NOT gate and also the truth table. Nice simple truth table just to get us started. So when the input is low, the output is high, and we can actually see that. I'm just using the first gate here. So I've got the input tied low through a 1K resistor, and I've got the output here showing you this on this yellow LED, and you can see input's tied low, output is high. So if I just use a jumper to take the input high, out goes the LED. So input low, output high, input high, output low. So we're just confirming there that yes, the NOT gate is working. Now I'm sure the purists at this point would be keen to point out to me that when you're not using all the gates on a chip, you should have all the inputs tied low. Yep, I agree. I'm using this at incredibly low frequency, and it isn't going to be an issue, so I'm not doing that, although I do appreciate that that would be best practice if you were working at a higher frequency. Okay, so next chip along here, the 74LS02, which is at 4 NOR gates. That's not OR, and here's the symbol for a NOR gate and also the truth table, and you can hopefully see that the only condition that the output goes high on a NOR gate is when both inputs are low. So when either input is high or low, you're getting nothing, and when both inputs is high, you're also getting low output. So I've currently got that set. The output here is there, that's that LED. So the output's high, and I've got I've got both inputs tied low. And so yes, that's proving the truth table. So if we just now use our jumper again and take one of the inputs high, like so, that should go out. There you go. And if we try taking the other input high, that should also go out. And just to prove we are really getting what we're saying, let's take another high, and let's take both inputs high there. Yeah, the LED stays out, so the output is low. So that confirms the truth table. So both inputs tied low gives us an output as per the truth table. And then on the right hand side here, I've got a 74LS86. That's a quad XOR gate, an exclusive OR gate. Exclusive OR is something that got used at, in the Enigma machine to encode messages. It's quite an interesting subject if you're into that kind of thing. So here it is connected up. The output of this gate is on pin 3, the inputs are on pin 2. So I've got one input, well actually I've got both inputs here tied low. So if we look at the symbol and we look at the logic gate with both inputs low, we should have nothing, which is correct. And then with both inputs high, we should get also get nothing, but with either input one high and one low, we should actually get an output high. So let's just try that. Let's just try taking one of the outputs high. Yeah, so on she comes, and let's just try the other one. Yeah, so that's working from the truth table point of view. And then if we take both inputs high, the output should be low, and indeed it is. So that's the exclusive OR gate. So I just wanted to show you that working, and I've picked the NOR gate and the exclusive OR gate for no other reason than I've done videos before on logic gates, and I've always used things like NAND and AND, the really common ones, and these are a bit more obscure, so I thought, yeah, well, why not? So let's now have a think about how we can use a signal generator to explore what's going on here. So to do that, I'm just going to reposition the camera and then we'll carry on. Okay, so these 74 LS logic chips use a 5-volt supply, and they also consider logic high to be something above 3 point something volts, and logic low, I think it's below 2 point something volts. It's in the data sheet, it doesn't matter for the purposes of this morning. However, let's just look at how we're going to use the signal generator with these chips. So what I've got here is I've got a square wave set up, and I've picked an amplitude of 5 volts, and if I now turn on channel 1, we get a nice square wave alternating between logic 0 and logic 1. So we can use that to supply the inputs of the chips to look what happens when we are changing the state of each gate. Or can we? Now, if you're a bit more experienced, you've, I'm sure, already spotted that this isn't going to work, but there is a nice bit of learning here if you're new to signal generators and scopes, in that at the moment I just pressed auto setup, and it's the scope just picked up the waveform like that. So if we now look at how it's coupled, it's actually coupled on AC. So if we I've managed to turn off channel 1 there, apologies. So we've got AC coupling, but what we need to do here for this is we actually need to go to DC coupling. So let's just select DC coupling. Now you might be tempted to say, well, that doesn't look any different. Well, the shape of the waveform isn't any different, I agree, but if you look here at the 0 point, that hasn't changed either really, except that we're now in DC coupling, and so that means that's 0 volts, and actually that's plus 2.5, and that's minus 2.5, and that isn't what we want. What we actually want is 0 to 5. So to do that, on the signal generator, or certainly on the Junctek here, we've got an offset setting. So if we press offset, we can now change that. So I'm going to change that to 2.5 volts, which is there, and we've now vanished off the screen. So let's just reduce the y-axis a little bit so you can actually see it. So now what we've got is we've got 2 volts per division, so we've got 2, 4, 5 volts. So it's now going from 0 there to 5 volts. So that's just an important thing to bear in mind. You do need to use that offset because your chips won't appreciate having minus 2.5 volts put on them. The hex inverter, when I was setting this up, actually did survive that, but it certainly isn't good practice. So if you're going to be using square wave output, make sure you've set the offset, and if you're checking it on your scope, make sure the scope is in DC coupling so that you do actually see what's really going on, and we've got this 0 to 5 going on and not plus or minus 2.5. Right, let's reposition the camera and look on the circuit board what we can do with those waveforms. Okay, so apologies first of all if I put my hands in front of the breadboard occasionally. It's probably unavoidable to show you this. So what we've got is we've got output from the signal generator being fed in here, and if I switch channel 1 on, we've got that blue LED there which is flashing, and actually I've got a frequency of 1 Hertz, so it's flashing once a second, and I've done that kind of speed so that you can see what's going on. So if we now take, do my best to not cover up too much of the picture for you, if we now take that. And so we've got a hex inverter here which is currently tied low, so obviously we've got a positive going pulse of 5 volts. So if we put that onto the input of the hex inverter, just to prove how the circuits are working here, so we've got the inverter doing its job. So when the blue LED is on, the LED is off, and vice versa, and that's the NOT gate doing its stuff. Okay, let's now look at some of the other gates. So what I'm going to do, so there isn't too many LEDs for you, is I'm just going to remove the inverter LED, because I just wanted to be able to first of all prove the circuit was actually working. So let's feed the clock into one of the inputs of the second gate, which is the 74LSO2. That's the NOR gate, and I've currently got one input here, well, both inputs tied low. So let's take one of the inputs high. Let's take that first one high, if we can manage that. There, yeah, and we appear to be just getting exactly what we got with the NOT gate inversion, and indeed that is the case. If you can remember back to the truth table, when one of the inputs is low and one is high, then the output is low or high depending on which one you choose. So that is at that point acting like an inverter. So let's now take a slightly longer jumper, and I'm going to struggle for space, so I do apologise, but hopefully it'll make some sense. Let's go right across now to the third chip, which is the 74LS86. That's the exclusive OR gate, and I've got again I've got both inputs tied low. So let's take one high, and you can actually see the difference here between a XOR, a NOT, a NOR, and an XOR. We've got those two actually in synchro, whereas that's inverted. So really the point of this was to show you how you can use your signal generator generating a positive going 5 volt pulse with nothing below the zero rail to work logic circuits. Now it's quite common when using chips like this to have some kind of perhaps clock signal, which would be running at kilohertz, megahertz even, certainly quite fast, certainly too fast for us to see an LED flashing. But let's just assume that channel 1 there now is a clock, and it's providing its clock signal to at least one of the inputs of the chip, and our circuitry requires us to perhaps change the state of the output depending on the condition of a couple of inputs. Okay, so now what I'm going to do is I've got channel 2 set up with an identical square wave, positive going 5 volts, so that's 5 volts square wave with the 2.5 volt offset, and I've got it at 0.5 hertz, or once every 2 seconds if you like. So I'm going to switch channel 2 on, and hopefully you can see there that the green LED is flashing at half the speed of the blue LED. So let's now apply some of those signals to the other sides of the gates, and hopefully you should see a flash pattern which would agree with the truth table. So if I start with the NOR gate there, and so now we're only actually getting, with the NOR gate, we're only getting the LED coming on when both inputs are low, and obviously that requires the signals to be both low at the same time. And then if I do the same thing for the exclusive OR gate, what you can now hopefully see, we've got nothing's changed here with the two input frequencies, but we've now got completely different flashing pattern for the NOR and the exclusive OR, and obviously they're both in line with the truth table. So the point of this was to get a few LEDs flashing. Why not? There's plenty of Arduino projects do that, and why not indeed. But hopefully what this is showing you is how you can make use of signal generator to explore what's going on with logic chips. And as I mentioned earlier, I've done several videos on digital electronics, where I've done quite a few videos on counters, for instance, and I've been using a Siglent generator in exactly the same fashion with that 2.5 volt offset, so we've got a positive going signal, doesn't go below the line. Okay, well that's it for our look at using a Siglent generator with digital electronics, and hopefully you've found it useful and it's made some sense. In particular, the notion that these digital waveforms usually go from 0 up to a positive voltage, depending on the particular semiconductor that you're using, and so that's certainly worth bearing in mind. Save a little bit of confusion perhaps sometimes if you're working with stuff on the breadboard. If you're in the market for a multimeter, please check out the Kaiweets multimeters. There's some links below in the description, and there's also a code you can use, gives you a discount and also helps the channel. I find these Kaiweets multimeters to be more than adequate for use with hobby electronics, and in fact I use mine extensively, both here in the lab and also with some of the other things that I do that require some measurements. So check them out and see what you think. Thanks very much for watching, and look forward to seeing you on the next video.